Hello guys, this is the second lecture of our chapter number 11, that is transport in plants. Yesterday we have discussed different means of transport in the plants, that was diffusion, active transport, facilitated diffusion. Now we'll discuss plant water relations. It is one of the most important lectures, and I am your teacher Naman Trivedi here, and we'll start with the topic of plant water relations. So we'll also discuss water potential, osmosis in this lecture. Both are highly important topics. Now the first few part you are supposed to read it from the textbook. So as they was mentioned that water is the main medium in which the substances are dissolved. Water is the main medium in which the substances are dissolved, and it is also a medium for transport as such. Okay, and if you talk about the protoplasm basically is formed by the organelles as well as the cytoplasm, also has different molecule dissolved. And protoplasm, again if further we go and if we take the cytoplasm also contains mainly 70% of the water, as in a single cell 70% is water approximately. Now they have given certain examples. That is, first they are mentioning about the watermelon. Watermelon has 92% of the water, whereas other herbaceous plants can have 10 to 15% of their fresh weight as dry matter. That means when you take a plant, you remove all the water from it, then the 10 to 15% of the fresh weight, okay, that is contributed by the water. So water contributes to 10 to 15% of the fresh weight of the plants. Fresh weight is a weight which includes the water, and dry weight does not include the water. So when you completely remove the water, that means when it is dehydrated, then what you see is everything except the water. So remember that even as a dry matter also, the 10 to 15% of the fresh weight was contributed by the water. Now next part is mainly we'll discuss about the distribution of water within plants. As they mentioned, the woody plants have relatively very little water, and soft parts mainly contain water. Okay, the soft parts will mainly contain water, as we know that. So now further going on to that part, if you talk about the seed, so a seed may appear dry but it will still have water. Okay, so you cannot really judge from the appearance if a dry part whether it contains water or not. Now they've given the definition of transpiration. So as we know that terrestrial plants, they lose water through the evaporation, and it will go in the surrounding atmosphere or air, and that's why when we stand beneath the plant we feel a cool breeze, or we feel the coolness, and the reason is basically the huge amount of water which is lost through the air by the process of evaporation. I hope you all know evaporation, you might have studied that in the lower standard. Now for questions from the further part, they will ask about the watermelon, how much water it contains. They may also ask how much water is lost. So over here they mentioned that a mature corn plant can lose 3 liters of water in a day, while a mustard plant can absorb water equal to its own weight in about 5 hours. So they may ask you that, let's say the weight of the mustard plant is the biomass or the weight of the mustard plant is, let's say, 10 grams. So what amount of water will it absorb? Okay, then the answer will be the same. It will be the absorption of water by mustard plant will be equal to its own weight. Okay, so remember that a mature corn plant can almost lose 3 liters of water in a day. So that's why water is very important factor, okay, for productivity in both agricultural and natural environments. Okay, without water plants cannot survive. So from this, remember the definition of transpiration, remember about the corn plant, remember about the watermelon, and also remember about the mustard plant. These four things are highly important. Mustard plant question has been asked quite a few times. Now this water loss which happens through the air, it will be mainly by the stomata, which we'll discuss further. Now we are moving on to one of the most important topics of this chapter, and as such also slightly difficult to understand, but I'll make it as easy as I can. This topic is as such based on chemistry and physics, more of a chemistry, but it's very much important to understand the relations of water and plant and the movement of the water. Now over here they have given a concept which we call as psi W. So psi W is something which is what we call as water potential. Okay, now to understand these things, okay, you need to know that water molecules has energy, they possess kinetic energy. For example, if there is a dam, let's say there is a dam, in that dam there is water, so that water has energy. Now if you allow this water to fall from certain height, water molecules will basically come in motion, and that potential energy of the water will be converted into kinetic energy, and that kinetic energy can move the turbines and can produce electricity. So just imagine how much energy water has. Okay, so just imagine how much energy water has. Also, if you, I'll give you another example, those who know a bit of swimming. Okay, so whenever you jump from certain height in a swimming pool or in a water source, then you have to jump as if your legs will be undergoing. You should not jump with your head undergoing down, because if your head directly hits the water, it is really painful. So that is because water contains energy. Your momentum mass also plays role, but water also has energy. So that's why water will always contain energy. Now to understand this, I'll just take my notes so that it will be easier for you. Okay, so here we are talking about the water potential. So water potential can also be termed as chemical potential. We denote it by psi. Okay, so here we'll discuss three things: psi s, psi p, and psi w. Now psi s stands for solute potential. Okay, psi p stands for pressure potential, and psi w stands for water potential, as you can see over here. Now as we know, water molecules possess kinetic energy. Water molecules possess kinetic energy. So this energy is in relation to what we call as the concentration of pure H2O molecules. This energy is in relation to the concentration of pure H2O in the system, as you can observe it over here. Okay, so it tries to denote that the energy which we are talking about, greater the concentration of H2O, greater the kinetic energy. So it is as such directly proportional. Greater the concentration of H2O in the system is directly proportional to the kinetic energy. I'll also share my notes in the group. Okay, so you can take it out. There has been no response from your side, either your career point classes are going on or something. I'm not sure whether something else, but anyways, I'll be doing my work. I'll be putting whatever I'm supposed to do, and if you have any doubts or anything, you can drop me a message. So greater the kinetic potential, greater the energy. Now pure water will have highest water potential. Pure water will have highest water potential. Now technically pure water is not possible. Why? Because water will always have some minerals or something dissolved in it, unless you prepare it industrially, milky or millipore water. Then except that, completely water with only H2 is not possible, because water has properties, everything, a lot of the things will dissolve in it. So as such, the H2O movement will always from higher psi W to lower psi W. So it will be always from where the psi W is high to where psi W is low. So water movement will always from higher psi W to lower psi W. We always represent this potential in the form of pascals. The unit is pascals, just like pressure. We can have megapascal, kilopascal. Okay, So for pure water at standard temperature, that is if you know about the STP, so you're taking standard temperature, psi W will be 0 and pressure we will consider at that conditions as 0. So psi W equal to 0 at standard temperature, and pressure is also equal to 0, and pressure is also equal to 0. Now for a liquid solution or for aqueous solution, we always consider psi W as negative because it is responsible for movement of water molecules from a region of higher concentration or higher psi W to lower psi W, and the movement will happen till this both the solution will have equal psi W. So let's say this is psi W A and this is psi W B. So if both are separated, then the movement will continue till the water potential of both the systems will become same. Till the water potentials of both the systems will become same. That is, water will move from a region of higher water potential to a region of lower water potential. So as such, when we consider psi W, it is always total of solute potential, pressure potential and metric potential. Now metric potential is we consider for the seeds, it is not part of your syllabus, which we call as the psi m. Your textbook only mentions that this is mainly psi W plus is equal to psi s plus psi p. That is, water potential is equal to solute potential plus pressure potential. So this brings us to discuss solute potential, or what we call as psi s. Psi s can also be termed as osmotic potential. Psi s can also be termed as osmotic potential. Okay. So now we'll understand the psi s because it is integral part to understanding the water potential. Yeah, excuse me. Just a moment. So let's assume a condition that we have some water, and as I told you, it is almost difficult to find completely pure water. So always there will be some solute which will be dissolved in water. So if I'll dissolve solute in the water, then the number of free water molecule will decrease, and that's why the psi W will also decrease. So if you dissolve the solute in the water, okay, then the free water molecule will always decrease, because when solute is added to the water, some of the water molecules will get bound to the solute, and that's why the pure H2O molecules will decrease. Listen to my words very carefully, because all these descriptions is not appropriately given in the textbook. So to understand the concept and everything, you need to listen to what I say very carefully. I also share the notes on the group later, so just go through that. Now if you talk about solutions, then all the solutions have less psi W than pure water. So pure water has maximum psi W. So we can say that the pure water has maximum psi W. Why it is so? Because pure water we only consider H2O. Whenever we take any solution, that means solutes are dissolved in that water. Whenever we take any solution, that means solutes are dissolved in that water. Now when we dissolve the solute, it will become a solution, and that's why the number of total H2O will decrease because of its reaction with the solute, or because of its association with the solute, and hence always all the solutions will have lower water potential or psi W than pure water. That's why we call that pure water has maximum psi W. Pure water has maximum psi W. Remember that. So you need to know one thing, that more solute means psi s is more negative. Less solute means psi s is less negative. That means if I'll take psi s for particular solution as -3 and psi s for particular solution as -5, then remember that if psi s is more negative, that means it has lower solute potential. If it has less solute, it is less negative. So here if you consider -3 and -5, okay, so -3 as less solute, so -3 psi s will be greater than -5 psi s, will be greater than -5 psi s. Less solute, less negative. More solute, more negative. Now this will be with the normal sign convention. This will be with the normal sign convention. If let's say I have given you another, I'll take another example, that psi s, okay, let's say I'll take another example. Psi s of one solution is -4 and psi s of other solution is -8. So now you have to find, if you have to inform me that which one will have higher solute potential, which one will have higher solute potential. So there is a simple logic. More solute means psi s is more negative, okay, and less means less negative. So here the answer will be -8 is bigger than -4. It is not like the usual sign convention which we use in the mathematics. It is not like the usual sign convention which we use in the mathematics. Remember that. So -8 will have more psi s in comparison to -4 psi s, because it is more negative, and this is the -4 one. The -4 one was less negative. Remember that. If you have any doubts, you can still put it in comments, or you can ask, you can drop me a message to understand it. So at atmospheric pressure, psi w equal to psi s. Now that means whenever we apply a pressure greater than atmospheric pressure, okay, the psi w will increase. Whenever we apply a pressure greater than atmospheric pressure to pure water solution, the psi w will increase. You might have studied in psi s equal to CRT in chemistry, that C is concentration of solute, again in moles per liter, and R is gas constant, not universal gas constant, and T is temperature. So it is in relation to that. Now coming on to the last part in this, that is mainly pressure potential. So pressure potential mainly denotes hydrostatic pressure, and it is denoted by psi p. Okay, so pressure is mainly generated by diffusion of water into the cell. That is, when water comes from outside to the inside in the cell sap or in vacuole, it generates pressure potential, or psi p. Now this is very much related to turgidity of the cell. That is, when water will enter inside the plant cell by diffusion. This is when water will enter inside the plant cell by diffusion, it will build up the pressure. It will build up the pressure against the cell wall of the plant cell, and thus the plant cell will become turgid. And hence the plant cell can maintain its shape. So this is what turgidity means. Okay, and it is by entry of water by diffusion inside the cell. So what will happen? The entry of water will increase the pressure potential, and this positive value of psi p is called Turgor pressure, and this positive value of psi p, that is positive value of psi p, is called Turgor pressure. This positive value of psi p is called Turgor pressure. Okay, so usually psi p is positive, whereas in plants psi p can be negative. Okay, why? Because of the tension in water column. So as such, psi w or water potential can be affected by both, that is by psi s and by psi p. So psi s and psi p is equal to psi w, and both of these can affect water potential. Both of these can affect water potential. Metric potential is not as such mentioned in the syllabus. It is anyhow, I'll tell you, it is basically psi m. It is because of the addition of water molecules. Okay, is always negative. It is always negative. It is for newly developing seeds, we consider it. Remember that. Now here we have to understand few things. That is, for a plant cell, because the questions has been asked, that is OP, TP and WP. OP stands for osmotic pressure. TP stands for Turgor pressure, and WP stands for wall pressure. WP stands for wall pressure. So we denote OP as osmotic pressure, TP as Turgor pressure, WP as wall pressure. Now if you take any of the plant cell, then always, if you want to see the directions of the osmotic pressure, that is water coming on the inside, it is in this direction. That is OP is in this direction. So OP will be in this direction, that is towards the inside. Now Turgor pressure, or what we call as the turgidity of the cell. So Turgor pressure will be towards the cell wall. Turgor pressure will be towards the cell wall. And the wall pressure, or what we call as WP, is also exerted from the wall. Towards the inside. So I'll take one by one. Okay, I'll take one by one, just so that it will be easier for you to understand. This is what OP is. Okay, this is what OP towards the inside, as you can see, for a plant cell in which the water is entering. Now let us assume and let us talk about the TP. So TP is over here, and TP you can see is in this direction towards the wall. TP is always, you can see I'm making the arrow darker so you can understand. So TP is always the water which has entered inside the cell. It is exerting pressure onto the wall. That is what we call as Turgor pressure. Finally we have WP. Okay, so this is just a moment. Finally we'll talk about the WP. Now if you talk about the WP, it is always, you can see in this direction, this is WP is always in this direction. It is exerted by the wall in counter to the Turgor pressure, and wall pressure is always equal and opposite to psi p. It is always equal and opposite to psi p, remember that. Now this will be useful for the concept which we are going to understand. So there is something termed as diffusion pressure deficit. Just a moment. There is something termed as diffusion pressure deficit, as you can see over here, or what we call as DPD, or what we call as DPD. It is basically nothing but it is the old term for water potential. Earlier, in physics and chemistry, the term to explain the water movement from roots to the tip of a leaf and all, DPD was used. Now, pure solvent or water has maximum diffusion pressure. That is, if I take, let's say, two systems, one in which I have dissolved the salt, another there is only pure water. So psi W will always be more of the pure water. The one in which I have dissolved salt will have less psi W. Why? Because salt is solute, and solute, if I dissolve in the water, it will decrease the pure water or pure H2O molecules. So the maximum diffusion capacity will be in the pure water, not in the sodium chloride solution, not in the salt solution. Remember that. So just a moment, excuse me. Yeah. So any fall in diffusion pressure of a solution, in relation to pure water is called DPD, and DPD will always be equal to OP minus TP. DPD will always be equal to OP minus TP, remember that, or wall pressure. So when the cell is fully turgid, DPD will be equal to 0. When it is flaccid, psi p is equal to 0. Right now, just go through it. I'll explain this thing in the next lecture because it is a separate part. Okay. So they may ask you to calculate this DPD and all. So if Turgor pressure is 0, then DPD equal to OP minus 0 or OP minus TP. So DPD equal to osmotic pressure. When the wall pressure is negative, then again DPP equal to wall pressure always, as I told you, if wall pressure is negative, then it's minus WP. So you have to put this value minus WP in this instead of Turgor pressure. So diffusion pressure deficit will be equal to OP plus TWP. OP plus WP. For a flaccid cell, if you put it in pure water, water will move inside the cell. So DPD equal to OP minus TP. So remember, all these formulas will be useful for some questions. So these formulas are, you are supposed to just go through these ones. They asked one question in the previously asked questions that you are given two solutions, that is A and B. For A, they have mentioned that OP is 10. Okay, DPD and Turgor pressure is 7 atmospheric pressure. Sorry, just a moment. For A, atmospheric pressure is 10. For A, atmospheric pressure is 10. Turgor pressure is 7 atmospheric pressure. So DPD will be what? DPD is OP minus TP. So it will be 10 minus 7. So the answer is 3. So for solution A, it is DPD is 3. Now try to understand again the question, the solution number. We have solution B. Now solution B has OP is 8. For solution B, OP is 8, TP is 3. TP is 3. Now DPD will be what? So DPD is again OP minus TP. OP minus TP. So it will be 8 minus 3 equal to 5 atmospheric pressure. So here DPD is 5. Here DPD is 5. So for A, solution A, the DPD was 3. For B, it was 5. For B, it was 5. Okay. Now, water will move from which place to which place? That is our question. The question was from where the water movement will happen. Okay, from which solution the water will move. So, as you know, A has 3 and B has 5 as DPD. And now if you want to discuss about the water movement, water will always move from lower DPD to higher DPD. Will always move from lower diffusion pressure deficit to higher DPD. So water movement will happen always from A towards the B, because A has lower DPD and B has higher DPD. So it will always be from A to B. Now try to understand this thing over here. This means that water movement will always happen where there is less water potential. So dpd of 3 atmospheric pressure is higher than as such or lower than 5. So the second solution will need more water. So water will diffuse from A to B. It is always from lower dpd to higher dpd. So do not forget to calculate this. This is very much important and they have asked frequent questions from this. So that's all for this lecture. We end water potential over here. It is very, slightly complex. So read from the textbook and also then go through the notes. I'll share the notes in the group also. If you have any doubts, anything, ask me the question. Okay. Obviously, what I teach you in the classroom and what I teach through here is you cannot compare because this is nothing in comparison to that. So still, if you have any doubts, you can call me. You can drop me a message. Okay. And go through my notes. I'll share it in the PDF form. Read from the textbook. Okay. So thanks guys. That's all. Naman Trivedi here signing off. Take care.